In the previous lecture we were discussing about the change in entropy in various processes, adiabatic, reversible adiabatic. So, we will generalize that a little bit and we will discuss about a reversible polytropic process. A reversible polytropic process is defined by a process governed by the following relationship: PV to the power n equal to constant. When n, I give you some examples. When n is equal to 1, it is reversible isothermal process of an ideal gas, that is the so called Boyle's law. When n is equal to Cp by Cv, that is reversible adiabatic process of an ideal gas, and when n equal to 0, it is a constant pressure or isobaric, reversible isobaric process. So, if you now try to draw a PV diagram describing all these processes. So, when n is equal to, first of all let us take the two limits of constant pressure and constant volume, they are easy to draw. So, constant volume is this one, or let us change the axis. So, normally, and this is very important, normally we draw volume in the x axis and pressure in the y axis. The reason is that volume is that independent variable that we can vary in experiments. Independently varying pressure is not something which is easy to do. So, if now we draw constant volume process or constant pressure process, let us first draw. So, this is P equal to constant. So, this is n equal to 0. Similarly, V equal to constant you can figure out. N is equal to plus minus infinity, V equal to constant. Then we will consider reversible isothermal and reversible adiabatic process. So, just let us try to get the slope of this diagram. So, just take log of both sides, you have ln P plus n ln V is equal to ln C. So, now if you differentiate both sides, so you have dP by, so you have dP dV is equal to minus n P by V, right. Pressure and volume they are both positive, n is positive, right. I mean, when we are talking, n could be actually anything, but when we are talking about comparison between isothermal for an ideal gas and adiabatic for an ideal gas, in one case n value is 1, another case n value is Cp by Cv, both of those are positive. Those examples will have n equal to positive. So, that means in those examples, first of all dP dV is negative, that means it is quite obvious from physical intuition that if you increase volume, the pressure will reduce for a given system. So, the slope of this is negative, not positive, okay. Now, if n is higher, then the magnitude of the slope is more, right. So, let us say, let us consider example of air. So, Cp by Cv for air if you consider calorically perfect gas, it is about 1.4, okay, and for reversible isothermal n is equal to 1. So, for reversible adiabatic definitely the value of n should be greater than 1 because Cp is always greater than Cv. So, if n is greater than 1, then dP/dV magnitude for reversible adiabatic process of an ideal gas is greater than the magnitude of that for reversible isothermal process of an ideal gas. In other words, reversible adiabatic process in this PV diagram for an ideal gas is steeper than the reversible isothermal process in the same PV diagram. So, we can draw maybe, and in both cases so this is n is equal to Cp by Cv and this is n is equal to 1, okay. So, these are just some examples, you could construct more examples. I would like to now instead of PV diagram draw TS diagram for some of these processes, so that it will give you a nice visualization of the same processes in the TS diagram. So, first of all, isothermal process, reversible isothermal process is temperature equal to constant. So, n equal to 1 is this one. What will be the vertical line in this? S equal to constant, that is reversible adiabatic process, n equal to Cp by Cv. Then the two processes that are left are constant pressure and constant volume. So, let us see which one is steeper in the TS plane. So, remember we are considering reversible polytropic process with specific example of ideal gas. So, TdS is equal to du plus PdV. This is such a useful relationship that you can use for any process diagram to explain the diagram. So, for constant volume this is 0 for constant volume, and for ideal gas this is Cv dt, mCv dt. So, ds is equal to mCv, so ds dt is equal to mCv by T for constant volume, right. Similarly, for constant pressure we will use the other TdS relationship.
Sir, just one thing, while writing du equal to mCv dt, you told that it is an ideal gas, right?
It is an ideal gas, yes.
Du is mCv dt even if it is not an ideal gas because it is a constant volume process, right?
No, 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 du is mCv dt, it is true only for ideal gas, because the definition of du is based on so if you write, so the what is the definition of Cv? So okay, so what you are saying is for if the volume is constant, yes, if the volume is constant then it is true. If the volume is constant, that then you can write du equal to mCv dt for any substance, but if the volume is not constant, so this equation we are writing for any substance and then you are applying it for a constant volume process. So, before applying it to a constant volume process, if we write this, it is better to commit that we are writing for ideal gas. If we from the beginning commit that it is constant volume process, then it can be generalized. Okay. So then it is 0 for constant pressure process. So ds dt for constant, actually this should be partial derivatives, you know, I mean I have written ordinary derivatives just for your simplicity in understanding, but because you have kept volume as constant, that means you know you are differentiating S with respect to T with a constraint V equal to constant. So let us be technically a bit correct, dH is mCp dt, so mCp by T. In fact, for constant volume and constant pressure processes you can use this for any substance, okay. But you know this we are comparing for ideal gases, so ideal gas as a special case will also work fine. So now out of these two, first of all these are positive or negative, these slopes are positive because Cp Cv are positive and T is absolute temperature which is positive, right. So absolute temperature is positive, so there are many nice interpretations about it. Recall this, just I am giving as a side note, the efficiency of a Carnot cycle is 1 minus TL by TH, right. This we derived in one of our previous lectures. Now by second law of thermodynamics, the efficiency of Carnot cycle should be less than 100%, Kelvin Planck statement. So if that will be less than 100%, TL cannot be less than 0. So that is why the concept of absolute temperature comes, it cannot have a negative value. So attaining an absolute 0 is a physical impossibility, maybe you can go to very close to absolute 0, but you cannot attain absolute 0 here, because if you run a hypothetical Carnot cycle with TL is absolute 0, then its efficiency will be 100% and that will violate the Kelvin Planck's statement. So this is just a different approach of looking into the fact that why second law of thermodynamics does not allow you to attain absolute 0. Okay. So the moral of the story which we want to use here is that the temperature is positive. So both are positive, but you have, because Cp is greater than Cv, del S del T at constant pressure is greater than del S del T at constant volume. In this diagram what we require is del T del S, not del S del T, because it is Ts diagram not St diagram. So in terms of del T del S, you will have the del T del S at constant volume greater than del T del S at constant pressure. That means constant volume line is steeper than the constant pressure line. So constant volume is that yellow line and constant pressure is the pink line. So this is V equal to constant, this is P equal to constant. Okay. So these are nice physical visualizations of very common processes that we come across in thermodynamics. Okay. Now we will go to the next agenda item, which is change in entropy in an irreversible process. So, when we say change in entropy in an irreversible process, what we essentially intend to mean is as follows. So, let us consider say a TS diagram. You have 1 to 2 a reversible path. From 2 to 1 you construct a reversible path. So, this is reversible A, this is reversible B, but you also construct an alternative irreversible path which is path C. From the Clausius inequality for reversible cycle, cyclic integral of del q by t equal to 0, that means 1 to 2 del q by t via path A and two to 1. So, let us write it reversible by path B, this is 0. For irreversible cycle, and if one of the processes in the cycle becomes irreversible, it becomes completely irreversible cycle. So, cyclic integral of del q by t is less than 0. So, that means del q by t from 1a to 2a by reversible path plus irreversible path, this is less than 0, right. So, now if you combine these two, so you can write that from these two combination del q by t integral along irreversible path 2c to 1c must be less than del q by t integral from, so this is b, right, I have mistakenly written as a 2b as to 1b. This is reversible. Because this is reversible, we can write this thing as equal to ds between 2 to 1. The formula del q by t equal to ds we can apply only for reversible process, and because it is between 2 to 1 and it does not depend on path, the same thing we can say that this is ds from 2b to 1b, right, because it is no more path dependent. So, to summarize that we can write, so this even if we write in place of c, that works, in place of b if we write c, that also works. The reason is between point 2 to 1 it does not matter whether it is path b or path c, it is the change in property. So, to summarize, we have C is any arbitrary path. So, we can replace C in working with mathematical expressions, we are more comfortable with equality rather than inequality. So, we can replace this inequality with an equality by writing that ds for any arbitrary path is equal to del q by t plus a positive number. This is called as entropy generation. So, this is greater than 0. It is 0 when the equality holds, that means it is 0 for reversible process. What is this T? This T is the temperature of the system boundary across which this del q is interpreted. Now, what is interpreted as a system? It depends on what is your domain of interest. Just like in mechanics, what is your free body diagram? It depends on you are representing forces on what, maybe one part or the entire system. So, here also what is your system? It depends on whether it is the machine itself or it is only the thermal reservoir or it is a combination of the machine and the thermal reservoir. Based on that, this T has to be appropriately substituted, because it is the temperature of that system boundary for which you are writing this equation. Okay.
Entropy generation is a path function, right? It depends on which path you go from one to two.
Entropy generation is a path function, yes.
I have written D.
So, you can just write, because you know this is I mean it is not a property. So, it is just you know just to make sure that these are differentials, but this is a path function. You can better write this as integral of, I mean that makes the real sense, because differentially you do not write it, you write this one, right. So, this is S2 minus S1. So, writing this as ds gen is little bit uncomfortable, because you know del q depends on the path. So, entropy generation depends on the path. In fact, it is very practical, because more irreversible the path is, more is the entropy generation. So, entropy generation is a physical measure of the extent of irreversibility. More irreversibility it is, more irreversible the process is, more is the entropy generation. So, here we have introduced entropy generation as a term which is positive, just to give the flavor of a mathematical equality instead of a mathematical inequality. But let us try to give a physical interpretation to this. So, we will discuss something which is called as lost work. So, lost work is a concept which, if expanded in English, will be lost opportunity of doing work. Okay. So, now when we say lost opportunity of doing work, what we mean? The concept is something like this. In a practical process, we always have an opportunity of deriving work because of a change in thermodynamic state. Now, if the process is reversible, that work derived is maximum. If it is irreversible, a part of the potential of deriving work out of the change in thermodynamic state is lost or destroyed. We will prove that how it happens. So, let us assume, let us consider two examples. One is you have a piston cylinder where the gas is moving in a quasi equilibrium process. So, if the gas is expanding in a quasi equilibrium process because of the heat transfer, then you have maximum work done, which is PdV, right. Let us consider another very interesting arrangement, same gas, but now partitioned in two places. On one side there is gas, another side there is vacuum, right. So, before the process starts, both of these hold the same potential of doing work, but if you now puncture this membrane, then this gas fills up this entire volume and no work is done. So, here delta W is equal to 0, because why no work is done? Because it is free expansion. So, I mean this is even a very philosophical way of looking into life. If we do hard work with resistance, then only we utilize our potential. If we do not do hard work and do not face any resistance and have a happy go life, then we do not utilize our potential. So, in this case the potential full PdV is utilized, in this case it is not utilized at all. Reality in life is something in between these two. So, reality is that you have PdV is equal to del W plus delta lost work, okay. So, this is any case in between, the work is between PdV and 0. So, PdV is maximum, the actual is less than that, and the balance is a lost opportunity of doing work, right. So, now you can write TdS is equal to du plus del W, sorry PdV. This you can use for any process, right. Then for PdV you can write del W plus del lost work, and from first law you know that del Q is equal to du plus del W. So, you can write TdS is equal to del Q plus delta lost work. So, ds is equal to del Q by T plus delta lost work by T. Compare this with ds is equal to delta Q by T plus delta S generation. So, this is nothing but entropy generation. Because entropy generation is positive, the lost work is also positive, and this term is 0 if it is reversible. That means with every irreversible process we have a lost opportunity of doing work. This is a physical interpretation of the entropy generation, which is associated with a lost opportunity of doing work. Let us stop here today. We will continue with discussions on entropy and possibly some problem solving in the next lecture. Thank you very much.